They had fired thousands of shells into the sky over the previous months, watching them explode in black puffs around enemy aircraft, calculating lead times and altitude settings with slide rules and mechanical computers. The gunners aboard the anti-aircraft cruiser USS San Diego had become expert at their trade through repetition and mathematics. On the morning of January 5, 1944, off the coast of New Britain in the southwest Pacific, they prepared to engage Japanese aircraft with ammunition that looked identical to what they had been firing for years. The shells were 5-inch, 38 caliber rounds, the standard anti-aircraft projectile for United States Navy vessels. Each round weighed 54 pounds. Each contained a mechanical time fuse set before firing to detonate at a specific altitude. The gunners had no reason to expect these rounds to perform differently than the thousands they had fired before. But inside a small percentage of the shells being loaded that morning was a device so revolutionary that it would fundamentally change the mathematics of anti-aircraft warfare. The device was called the VT fuse, though the letters stood for nothing in particular. They were a deliberate obfuscation, a cover designation to hide what VT actually meant: variable time, or more accurately, proximity. The fuse contained a miniature radar transmitter and receiver, a vacuum tube circuit, and a battery, all packaged into a space smaller than a man's fist, all designed to survive the incredible acceleration of being fired from a gun. When the shell left the barrel, experiencing forces exceeding 20,000 times the force of gravity, the fuse activated. As the shell flew toward its target, the fuse transmitted radio waves. When those waves bounced back from a nearby aircraft, the fuse detonated the shell. No calculation of lead time was required. No precise altitude setting was necessary. The shell simply exploded when it got close to the target. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The gunners on the San Diego did not know all of this. They had been told only that some of their ammunition was experimental and that they should fire it exactly as they would fire any other round. They did not know they were about to witness the opening shots of a technological revolution that would make anti-aircraft fire 5 times more lethal than it had been just months earlier. They did not know that the device inside some of their shells represented one of the most closely guarded secrets of the war, a secret considered so valuable that its use was initially restricted to overwater combat zones where enemy forces would have difficulty recovering unexploded shells for examination. They knew only what they could see through their optical sights, Japanese aircraft approaching the task force, and what they had been trained to do: fire shells set to explode at calculated altitudes in the hope that the blast fragments would intersect with the target. The mathematics of that hope were not encouraging. A standard mechanical time fuse, set to detonate at a specific altitude, created a lethal fragment pattern approximately 30 feet in radius for a 5-inch shell. The shell had to explode within that 30-foot sphere to have a reasonable chance of damaging an aircraft. Calculating where that sphere should be positioned in 3-dimensional space, accounting for the aircraft's speed, direction, and altitude, accounting for the shell's trajectory and time of flight, accounting for wind and atmospheric conditions, required extensive training and practiced coordination between rangefinders, plotters, and gun crews. Even with expert crews and the best mechanical fire control, computers available in 1944, the hit probability was low. American estimates suggested that approximately 2,000 5-inch shells were required, on average, to destroy a single aircraft using conventional time-fused ammunition. The expenditure rates were staggering, the success rates disappointing, and the fundamental problem was mathematical. The target was moving in 3 dimensions. The explosion was fixed at a predetermined point. The two had to intersect precisely in both space and time. The problem of hitting aircraft with exploding shells was not new in 1944. It was as old as military aviation itself, dating back to the First World War, when anti-aircraft guns were first deployed in significant numbers. Early anti-aircraft shells used impact fuses, detonating only when they struck something solid. This was clearly inadequate. An aircraft presented a small target, and the chances of a direct hit were vanishingly small. Artillerymen quickly adopted time fuses, mechanisms that could be set before firing to detonate the shell after a specific interval. Theoretically, at the altitude where enemy 2PTC aircraft were flying, the time fuse represented a significant improvement, creating a lethal radius around the explosion point rather than requiring a direct impact. But the mathematics remained difficult. Setting a time fuse required knowing the target's altitude, calculating the shell's time of flight to that altitude, and setting the fuse mechanism accordingly. By the time the shell arrived, the target might have changed altitude, changed direction, or simply moved out of the lethal radius. Fire control became increasingly sophisticated through the interwar years and into World War II. Mechanical computers, essentially complex assemblies of gears, cams, and calculating mechanisms, automated much of the prediction process. Operators fed in target range, altitude, speed, and direction. The computer calculated the required gun elevation, traverse, and fuse setting. The system worked after a fashion, but remained fundamentally limited by the fact that the explosion point was fixed at the moment of firing. If the target maneuvered after the shell was fired, if the altitude estimate was incorrect, if atmospheric conditions differed from the standard values programmed into the computer, the shell exploded harmlessly in empty air. The United States Navy had invested heavily in fire control technology. The Mark 37 Director, introduced in 1942, was among the most sophisticated anti-aircraft fire control systems in the world. It incorporated radar, ranging, optical tracking, and mechanical computation. Trained crews could engage targets with reasonable accuracy, but reasonable accuracy still translated to thousands of rounds expended per aircraft destroyed. The limiting factor was not the guns, not the shells, and not the fire control systems. The limiting factor was the fundamental nature of the time fuse itself. It detonated at a fixed point in space. The target was not fixed. It moved, maneuvered, and actively tried to avoid the predicted positions. What was needed was a fuse that could adapt, that could sense the target's proximity and detonate at the optimal moment, regardless of small errors in prediction. What was needed was a proximity fuse. The concept of a proximity fuse was not new. Engineers had been thinking about such devices since the early 1930s. The theoretical advantage was obvious. If a shell could detonate automatically when near a target, the precision requirements for fire control would be dramatically reduced. The lethal radius would effectively follow the target rather than waiting at a predetermined point. But the practical challenges appeared insurmountable. Any proximity sensing mechanism would need to fit inside an artillery shell, survive the acceleration of firing, function reliably at high altitude in varying atmospheric conditions, distinguish between the target and the ground or sea below, operate on battery power for the few seconds of flight time, and do all of this at a cost that allowed mass production. Early proposals included acoustic sensors that would detect engine noise, photoelectric cells that would detect changes in light intensity, and various mechanical or magnetic detection schemes. None proved practical for artillery shells. The breakthrough came from an unexpected direction: radio. In the late 1930s, researchers in Britain and the United States began experimenting with miniature radio transmitters that could fit inside a shell. The concept was simple in principle. The transmitter would broadcast a continuous radio signal. When the shell approached a target, the radio waves would reflect back. A receiver in the shell would detect these reflected waves. When the signal strength reached a predetermined threshold, indicating the target was close enough, an electronic circuit would trigger the detonator. Simple in principle, extraordinarily difficult in practice. The first challenge was the vacuum tubes. Radio circuits in 1939 required vacuum tubes to generate, transmit, and receive radio signals. Vacuum tubes were fragile glass, envelopes containing delicate filaments and electrodes. They were designed for stationary use in carefully controlled conditions, not for surviving the shock of gun firing. When a 5-inch shell is fired, it experiences acceleration exceeding 20,000 times normal gravity. Glass shatters. Filaments break. Electrodes shift position. The tube stops functioning. Engineers needed vacuum tubes specifically designed to survive artillery acceleration, tubes with reinforced structures, shorter and thicker elements, and entirely new manufacturing techniques. The Section T project, as it was, designated at the National Defense Research Committee, brought together scientists and engineers from multiple institutions beginning in 1940. The Johns Hopkins University Applied Physics Laboratory took the lead role in developing what would become the VT fuse. Researchers faced problems that had no existing solutions. They needed vacuum tubes that could survive 20,000 times normal gravity. They needed a power source that would activate instantly after firing and function for the brief seconds of shell flight. They needed a radio circuit simple enough to manufacture by the millions yet sophisticated enough to distinguish a target from background interference. They needed all of this to fit inside a fuse cavity approximately 1.5 inches in diameter and 5 inches long. The vacuum tube problem consumed months of intensive research. Standard radio tubes of the era used thin wire filaments suspended within glass envelopes. Under artillery acceleration, the filaments snapped like spider silk. Engineers tried thicker filaments, but these required more power than a small battery could provide. They tried shorter tubes, but standard tube designs didn't scale down effectively. The breakthrough came from reconceptualizing the entire structure. Instead of wire filaments, engineers developed tubes using metal ribbon filaments with extremely short lengths. Instead of delicate internal supports, they created rigid ceramic structures. Instead of conventional glass envelopes, they used specially formulated glass with higher impact resistance. The resulting tube, designated the WWII, was unlike any vacuum tube previously manufactured. It measured less than 1 inch long and 1/2 inch in diameter. Its filament was a tiny strip of metal barely visible to the naked eye. Its internal structure was reinforced with ceramic spacers. When tested in centrifuges that simulated gun-firing acceleration, the tubes survived. Not every tube, not even most tubes in the early production runs, but enough to prove the concept was viable. Manufacturing these specialized tubes required entirely new production techniques. Western Electric, the manufacturing arm of Bell Telephone, established dedicated production lines. Workers, many of them women with experience in delicate assembly work, learned to construct tubes under microscopes. Each tube required dozens of precise operations, each operation a potential point of failure. Quality control rejected tubes at stunning rates in early production, sometimes 90% or more. But gradually, through refinement of techniques and materials, the rejection rates decreased. By late 1942, Western Electric was producing acceptable tubes in quantities sufficient for field testing. The radio circuit itself presented different challenges. It needed to generate a radio frequency signal, transmit that signal through a small antenna, receive the reflected signal, amplify it, compare it to a threshold value, and trigger a detonator, all within the few seconds between firing and target proximity. The circuit needed to draw minimal power from a battery that had to be small enough to fit in the remaining fuse space. It needed to function across a wide range of DFM, temperatures and altitudes. It needed to ignore reflections from the ocean surface below, while remaining sensitive to reflections from aircraft above. Engineers settled on a design using 4 vacuum tubes in a circuit that was remarkably simple given what it accomplished. One tube served as an oscillator, generating the radio frequency signal at approximately 180 MHz. A second tube served as the radio frequency amplifier for the received signal. A third tube served as a detector and amplifier for the modulation envelope of the reflected signal. The fourth tube served as a thyrotron switch that would discharge a capacitor into the detonator when the signal strength indicated sufficient proximity. The antenna was a simple loop of wire around the nose of the fuse. The battery was a reserve type, activated by the acceleration of firing which forced an electrolyte into contact with the battery elements. The entire assembly, tubes, circuit components, battery, antenna, and detonator, fit into the fuse cavity with almost no wasted space. Every cubic millimeter was utilized. Testing began in earnest in 1942. Engineers fired shells containing prototype fuses at drone aircraft over the Chesapeake Bay. Early results were mixed. Some fuses functioned perfectly, detonating at the optimal distance from the target. Others failed to activate, failed to detect the target, or detonated prematurely. Each failure required analysis. Fuses were recovered from the water when possible, disassembled, and examined. Engineers identified failure modes, redesigned components, and tested again. The iteration process consumed months. By mid-1943, the VT fuse had achieved sufficient reliability for limited combat deployment. The decision to use it operationally came with significant restrictions. The fuse was considered so secret that its very existence was classified at the highest levels. Use was initially restricted to naval anti-aircraft defense over water, where unexploded shells would sink and be difficult for enemy forces to recover and examine. Use over land was prohibited entirely, even in remote areas, because of the risk that enemy forces might recover an intact fuse and learn its principles. Gunners and fire control crews received minimal information about the new ammunition. They were told only that certain shells were experimental and should be handled normally. They were not told how the fuse worked, only that it might improve hit probability. This secrecy served multiple purposes. It prevented information from reaching enemy, intelligence through captured personnel, or intercepted communications. It also prevented American crews from developing overconfidence or changing their firing procedures in ways that might reveal the existence of something unusual about the ammunition. The shells looked identical to standard 5-inch 38 caliber anti-aircraft rounds. The fuse cavity at the nose of the shell contained the VT mechanism, but externally there was no way to distinguish it from a conventional time fuse. Fire control crews set the guns exactly as they would for time-fused ammunition, calculating altitude and lead time using their mechanical directors. The VT fuse simply took over the final function, detonating at the optimal moment regardless of small errors in the calculated settings. Initial combat use began in the Pacific Theater in early January 1944. The cruisers, Cleveland and Montpelier, engaged Japanese aircraft using mixed ammunition loads, some rounds with conventional time fuses and some with VT fuses. Crews reported improved results but could not immediately quantify the difference. Combat conditions made precise assessment difficult. Multiple ships, fired simultaneously, hits were hard to attribute to specific shells, and the priority was destroying targets rather than gathering statistical data. But within weeks, a pattern emerged. Ships equipped with VT-fused ammunition were achieving aircraft kills with dramatically fewer rounds expended. The improvement was not marginal. It was not a subtle enhancement that required careful analysis to detect. It was obvious, unmistakable, and profound. The statistical analysis, conducted after sufficient combat data had been collected, revealed numbers that seemed almost too good to be true. Conventional time-fused 5-inch ammunition required an average of approximately 2,000 rounds to destroy a single aircraft. VT-fused ammunition required an average of approximately 400 rounds per aircraft destroyed. The improvement factor was 5-to-1. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The first large-scale test came not in the Pacific but in European waters during the Allied invasion of southern France in August 1944. Operation Dragoon, the amphibious assault on the French Mediterranean coast, involved hundreds of naval vessels, providing fire support and air defense for the landing forces. German aircraft, increasingly desperate and willing to accept heavy losses, attempted to strike the invasion fleet. The Luftwaffe, by August 1944, was no longer the dominant force it had been in 1940 or 41. Years of attrition over Germany, losses in Russia, and the systematic destruction of pilot training programs had reduced both the quantity and quality German air power. But the pilots who remained were often veterans, experienced in combat, and thoroughly aware that the invasion represented a critical moment in the war. They flew Junkers Ju 88s and Heinkel He 117s twin-engine medium bombers carrying heavy bomb loads intended for the ships clustered off the beaches. They flew Fokker-Wulf-Tful 190s and Messerschmitt Bf 109s, single-engine fighters tasked with protecting the bombers and strafing ground targets. They approached the fleet knowing that anti-aircraft fire would be intense. Every Allied ship, from destroyers to battleships, carried anti-aircraft armament. Fire control had been refined through years of combat. Crews were experienced. The Germans expected to face heavy fire. They did not expect what actually happened. Allied ships opened fire at maximum range using VT-fused ammunition in their 5-inch batteries. The German pilots, experienced in evading anti-aircraft fire, began their standard evasive maneuvers. They changed altitude, varied their approach angles, and used the vertical dimension to avoid concentrations of fire. These maneuvers had been developed through years of combat experience. They were based on a simple reality. Time-fused anti-aircraft shells exploded at predetermined altitudes, and a pilot who continuously varied his altitude made accurate fuse settings nearly impossible. But the Allied shells were not detonating at predetermined altitudes. They were detonating near aircraft regardless of altitude changes. A bomber at 8,000 feet, seeing shells bursting around him, would dive to 6,000 feet. The next salvo would detonate at 6,000 feet. He would climb to 10,000 feet. The shells would follow. There was no pattern to exploit. No altitude that provided safety. No evasive maneuver that reduced the probability of being hit. The mathematics had changed, and the pilots had no way of knowing why. German bomber formations approaching the Allied fleet off southern France suffered catastrophic losses. In a single day of operations on August 15, 1944, Luftwaffe units lost over 30 aircraft to naval anti-aircraft fire, a loss rate that exceeded 50% of the attacking force. Pilots who survived and returned to their bases reported that anti-aircraft fire had become inexplicably more accurate and more deadly. Intelligence officers recorded these reports, but had no explanation. The possibility that the Allies had developed a fundamentally new type of fuse was considered but seemed implausible given the technical challenges such a device would require. German technical intelligence had been aware of Allied research into proximity fuses since at least 1942, based on fragments of information gathered from various sources, but assessments had consistently concluded that the engineering problems were insurmountable. The idea that the Allies had not only solved these problems, but had deployed the technology in quantity seemed to strain credibility. Yet the evidence was undeniable. Aircraft were being destroyed at rates that could not be explained by improved gunnery or better fire control alone. The mathematics didn't work unless something fundamental had changed about the ammunition itself. By late 1944, German forces had recovered several unexploded VT-fused shells from various locations. Technical examination revealed the basic principle of operation, confirming what pilots had experienced in combat. The shells contained miniature radio transmitters and receivers. They detonated based on proximity to the target, rather than at a preset time. German engineers, examining the recovered fuses, were simultaneously impressed by the technical achievement and appalled by the manufacturing implications. The fuses contained vacuum tubes specifically designed to survive artillery firing. They contained batteries that activated on firing. They contained radio circuits of remarkable sophistication packaged into impossibly small spaces. The precision required to manufacture such devices in quantity suggested an industrial capacity that Germany, by late 1944, simply did not possess. Even if German engineers could replicate the design, even if they could solve the technical problems and create working prototypes, the Reich lacked the manufacturing capacity to produce such fuses in militarily significant quantities. German industry, by the final year of the war, was struggling to maintain production of basic armaments under sustained Allied bombing. Factories operated in dispersed locations to avoid air raids. Raw materials were increasingly scarce. Skilled workers had been conscripted into military service. The idea of establishing production lines for a device as complex as the VT fuse, requiring specialized vacuum tubes, precision electronics, and rigorous quality control, was simply not feasible. The disparity was not merely technical, it was industrial, economic, and, ultimately, strategic. The VT fuse represented more than just a clever device. It represented the productive capacity of an economy that could dedicate resources to solving difficult problems, that could manufacture precision electronics in millions of quantities, that could deploy new technology across multiple theaters of war within months of achieving production reliability. By the end of 1944, American factories were producing VT fuses at a rate exceeding 80,000 per day. Western Electric alone was manufacturing over 20 million vacuum tubes per year, specifically for proximity fuses. The supply chain that supported this production involved dozens of contractors and subcontractors, specialized materials from sources across the United States, quality control procedures that rejected components at rates that would have been economically unacceptable in peacetime, and a logistics system that delivered finished fuses to ammunition depots, loading facilities, and ultimately to ships and anti-aircraft batteries around the world. The Germans had nothing comparable. Japan had nothing comparable. The Allied technological advantage was not based on superior scientists or engineers, though the Allies certainly had excellent scientific talent. It was based on industrial systems that could translate scientific concepts into mass-produced hardware. The VT fuse was used extensively in the final year of the war across multiple applications. Naval anti-aircraft defense was the original use case and remained the primary application throughout 1944. By early 1945, with the risk of German technical examination reduced by the deteriorating military situation, VT fuses were authorized for use over land. Anti-aircraft defences in England used VT-fused ammunition against Von flying bombs, the pilotless aircraft that Germany launched against British cities beginning in June 1944. The improvement in hit probability was dramatic, increasing the percentage of V-1s destroyed, before reaching their targets. Field artillery discovered an unexpected application for the VT fuse in the winter of 1944–45. Artillery shells fused for proximity detonation could be fired against ground targets, detonating above the surface and creating airbursts that were far more lethal against infantry than shells that detonated on ground impact. During the Battle of the Bulge, American artillery batteries used VT-fused shells against German infantry advancing through the Ardennes forest. The shells detonated 15 to 20 feet above the ground, showering the area below with fragments. Soldiers in foxholes, protected from ground-burst shells by the earth around them, were exposed to fragments coming from above. The effect on German infantry formations was devastating. Units that had been trained to take cover from artillery by going to ground found that going to ground provided no protection. The fragments came from above, penetrating into foxholes and trenches. Casualties increased dramatically. German commanders reported that American artillery had become significantly more effective, but many did not understand why until much later. The psychological impact on soldiers under VT-fused artillery fire was profound. The sound was different from conventional artillery. Instead of the thump of shells impacting the ground, there was a sharp crack of airbursts. The fragments arrived from unexpected angles. Cover that had previously provided protection became inadequate. Soldiers experienced the same realization that Luftwaffe pilots had experienced months earlier, that the rules had changed, that tactics developed through years of combat experience no longer provided safety. In the Pacific theater, VT fuses were used extensively in naval anti-aircraft defense during the campaigns of 1945. The Battle of Okinawa, beginning in April 1945, involved the largest sustained kamikaze attacks of the war. Japanese aircraft, deliberately piloted into Allied ships in suicide attacks, represented a threat that conventional anti-aircraft fire struggled to counter. A kamikaze pilot, committed to reaching his target regardless of damage to his aircraft, would continue flying even after being hit, as long as the aircraft remained controllable. Destroying the aircraft required either catastrophic structural damage or killing the pilot. VT-fused shells improved the probability of achieving both. The shells detonated close to the target aircraft, creating fragment patterns that damaged control surfaces, engines, and cockpits. During the Okinawa campaign, naval anti-aircraft fire, using VT fuses, achieved kill rates against kamikaze aircraft that would have been impossible with conventional ammunition. Statistical analysis after the war estimated that VT fuses increased the effectiveness of naval anti-aircraft fire by a factor of 5 to 1 compared to time-fused ammunition, confirming the preliminary assessments from 1944. The story of the VT fuse is often presented as a triumph of American ingenuity and industrial capacity, and in many ways, it was exactly that. But for the individuals on the receiving end, for the German bomber crews over southern France, for the Luftwaffe pilots engaging Allied ships, for the Wehrmacht infantry in the Ardennes, and for the Japanese kamikaze pilots approaching the fleet at Okinawa, the VT fuse represented something different. It represented the moment when technology shifted decisively beyond their ability to counter it. The German pilot who changed altitude to evade anti-aircraft fire and watched the shells follow him to his new altitude experienced a realization similar to what Japanese tank crews experienced at Saipan. The equipment and tactics that had previously provided some measure of protection were no longer adequate. The enemy had deployed technology that changed the fundamental nature of the threat. No amount of skill, courage, or tactical expertise could overcome the mathematical advantage the VT fuse provided. The infantry soldier in the Ardennes, taking cover from artillery in a foxhole that had protected him during previous bombardments, learned that his understanding of battlefield survival was obsolete. The fragments came from above, penetrating his position, defeating the protection that earth and terrain had always provided. His training, his experience, his instincts about where to find safety all became unreliable. The realization was not gradual. It was immediate and terrifying. For the Japanese kamikaze pilot, the mathematics were even more unforgiving. He was committed to reaching his target regardless of damage. His aircraft could absorb significant punishment and continue flying as long as critical systems remained functional. But VT-fused anti-aircraft fire didn't require direct hits. It required only proximity. The shells detonated near his aircraft, close enough that fragments struck with sufficient energy to destroy engines, sever control cables, or kill him in the cockpit. The suicide tactic that had been developed specifically to counter the limitations of conventional anti-aircraft fire found itself facing a technology that eliminated many of those limitations. After the war ended, technical assessments of the VT fuse's contribution to Allied victory were conducted by military analysts and historians. The consensus was that the fuse had been one of the most significant technological developments of the war, comparable in strategic impact to radar and second only to the atomic bomb in the hierarchy of secret weapons. Production figures supported this assessment. By the end of the war, American industry had manufactured over 22 million VT fuses. These were distributed across naval anti-aircraft applications, land-based, anti-aircraft defense, and field artillery. The fuses were used in the European theater, the Pacific theater, and the China-Burma-India theater. They were fired from 5-inch naval guns, 90mm anti-aircraft guns, 105mm howitzers, and 155mm guns. The versatility of the technology, its applicability across multiple weapon systems and tactical situations, demonstrated the value of solving fundamental technical problems rather than developing specialized point solutions. The gunners aboard the USS San Diego, who fired the first VT-fused rounds in combat in January 1944, did not know they were participating in the debut of a weapon that would change anti-aircraft warfare fundamentally. They aimed their guns, calculated their firing solutions, and engaged the targets exactly as they had been trained to do. The shells did the rest, detonating at the optimal moment based on proximity rather than preset timing. The improvement in effectiveness was not immediately apparent to the individual gun crews. They saw targets destroyed, as they had seen targets destroyed before. But the cumulative statistics, compiled across hundreds of engagements, revealed the truth. The mathematics of anti-aircraft warfare had shifted decisively. What had required 2,000 rounds now required 400. What had been a weapon of area saturation became a weapon of precision. The device that made this possible fit in a man's hand, weighed less than a pound, and contained technology that German and Japanese engineers could examine but could not replicate at scale. The VT fuse was not just a technological achievement, it was a demonstration of what industrial capacity could accomplish when directed toward solving difficult problems. It was evidence that the material advantage the Allies possessed was not merely quantitative, but qualitative. They could build not just more weapons, but better weapons, and they could deploy those weapons in quantities that overwhelmed any attempt to counter them. For those on the receiving end, the lesson was the same lesson learned in countless other contexts throughout the war. The gap between what was needed and what was available, between what tactical skill could accomplish and what material superiority could impose, was unbridgeable. The VT fuse made anti-aircraft fire 5 times more lethal, not through better training or improved tactics, but through technology that changed the fundamental nature of the weapon. That same pattern, technology and industrial capacity overcoming tactical skill and fighting spirit, repeated itself across every theater and every domain of the war. The story began with gunners firing shells that looked identical to what they had fired before, unaware that the device inside would change everything. It ended with the statistical certainty that modern industrial warfare rewarded not just courage and skill, but the capacity to manufacture precision technology in millions of quantities and deploy it globally within months. The morning of January 5, 1944, off the coast of New Britain, marked the beginning of that change. The shells that were fired that day carried with them the future of anti-aircraft warfare, packaged into a fuse cavity 1.5 inches in diameter. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.